All right. So we're doing 8-1 tonight, 8-2 on Thursday, 8-3 on next Tuesday, and then 9-3. And then your test is the week before spring break. So basically 5 classes and then the tests. So it's a little quicker turnaround this time. I wanted to get the test in before spring break, so this way you don't really need to. We'll start after spring break doing something slightly different. So it's a nice little stop in there. And plus, I have to turn in the midterm grades at that point anyway, so it's nice to have at least 2 tests done before the midterm. All right, so we are basically done learning new integrations. So now, just like chapter 6 really used the basic integrations to do like area between 2 curves, and then we use that to find volume of shapes, we're going to look at how we can start using the integration to do things. Tonight, we're going to look at arc length and lengths of things. On Thursday, then we're going to take that and look at how to find surface area. So let's start off with a couple really, really simple ones. What's the length of AB? Okay, how'd you get it? So it's basically the absolute value. Yeah, you're finding the distance between them, right? So it's absolute value of -3 minus 7, which is 10. So how do you find the length of a line that would be diagonal? Okay. Let's use yellow. So if I make my triangle, got my triangle, what do I do next? So that's 7. And that's 2. Yeah, I know. All right. But what's the length of the line? I found the length of the sides of the triangle, but what's the length of the line? Oh, so close. Nope, you're missing one step. He's right. It is 2 squared plus 7 squared. Right. Because you're basically using a squared plus b squared equals c squared, right? So when you come over this side, when you solve it for c, it's the square root of a squared plus b squared. So it's the square root of 2 squared plus 7 squared. Okay. Oh, yeah, all right. I did screw them up. I blame him. There we go. There, better. So 25 plus 16 is 41. So it's the square root of 41. Okay. So to find the length of something, it's the square root of the endpoints. Now, that's just one straight line. What if I wanted to find out the arc length of a shape like this? So we would have to break it up into a bunch of points, right? And you could approximate it that way. And then if we broke it down into even more points, it'd be a better approximation, correct? So what would be the perfect approximation of it? If the things are getting smaller and smaller, we're in essence finding the integral of it. Because the integral is going to take the sum of all those pieces going up. Yeah, it's the limit, which in essence turns into the integral. So our wonderful arc length formula. The formulas are the exact same. One's in Newton's notation and one's in Leibniz. So actually, I'm going to make this a little bigger. I want to make the Leibniz one bigger because I can, because the other one is broken down. So that's that one. So the only difference between them, one is on the y and one is the x. Notice there really isn't any actual change in the setup of it. It's the square root of 1 plus the square of whatever the function is. Now you can start to see why we couldn't necessarily do this before chapter 7. Because we didn't have a way to deal with stuff underneath the square root that didn't have something I could pull out. Because you could end up getting something like 1 plus x squared in there. And then we have to deal with that. So, and that's where my trig identities and stuff like that that came into play in section 7.2 and 7.3 come into play. One's x and one's y. The upper two are dx and the bottom two are dy. It just depends on how you're which length you're looking for. You can actually do it. So if we're looking at this, it really depends on the direction that the shape is going, on how you want to break down the pieces for it. So is it the equation easier set up as y equals, or is the equation easier set up as x equals? So, but the process behind them is identical. There's nothing really different between the two. All right, let's do it. So we've got, we're looking at for the arc length of y squared equals x squared, which is this graph here. And we want to find it from 1, 1 to 4, 8. Notice this is not a perfectly straight line. Close, but not a perfectly straight line. So the first thing we have to figure out is which one do we want to solve it for? Do we want to solve this for y, or do we want to solve this for x? If y squared equals x to the third. Because it's not solved for either one right now. And this one, it doesn't actually make a difference. Let's solve it for y. So we have y equals. So to get y equals, I'm going to take the square root of x to the third. When I take square root, I got to do the plus or minus version of it, correct? So in this problem, which part do I want? Do I want the plus version or the minus version? I'm going to have the plus version. Okay. So that is going to literally depend on where we're looking at with our points. If I was looking at from 1 to -1 and 4 to -8, then I'd want the negative version of it. So we have to look back at the points to determine which one we would want in this situation. In this case, I want the plus one. Yeah.
Will there ever be a case where we have to like go for 2 segments, like a point and a positive and on a negative, and you have to like do them to the?
You split it. Yeah, you'd have if it was. So let's say we wanted to do this from 1 -1 to 1 1. That would have given us this piece right here. It would have given us this part right here. We could do that. You'd literally split it up and do it as two parts. You'd have used 0, 0 to 1, 1, and 0, 0 to 1, -1. And you'd have done two different integrals to just add the answers together at the end. So you wouldn't try to do that as one integration.
But you do it, it's like a double, it's like symmetric.
Yeah, in that case, that one is going to be symmetric. So yeah, you could do.
So I know there's a test for like the y-axis being symmetric.
Yeah,
How
even.
do you do it with the It's just not a function.
It's the opposite, actually. So to test if it's even, you plug in -x to the function. If it comes out to be exactly the same, it'd be even across the x-axis. I mean, sorry, the y-axis. You want to test it against the x-axis, you plug in -y. If it comes out to be the same, it's going to be symmetric across the x-axis. So it'll work the same way.
You could just like change the variable as if it was like.
Yeah. Yeah, you could just switch it. Yes, you could do it that way too. All right. So we've got that. Let's make this a little simpler just to. So we're going to make this as x over is 3 over 2. Let's make it so this way we don't have the square root inside of the square root and stuff like that. All right, so now we've got to use our equation. So my integral goes from a to b, square root of 1 plus f prime of x squared dx. And I know my f of x is x to the 3 over 2. All right. So the first thing I have to find is I have to find the derivative. So I need f prime of x. So what's the derivative of x to the 3 over 2? Yeah. So remember, derivative, you bring down the exponent, subtract 1 from it. So this is going to be x to the 1 half. And we need to figure out what a and b is. So in this case, we're looking at the x's, so we're going to go from 1 to 4. So my integral is from 1 to 4, square root of 1 plus 3 over 2 x to the 1 half squared dx. All right, we good up to that point? Now we just got to do our integral. So let's try to clean up the inside as much as I can, simplify it down, and see what method I need to use to solve this one. So I have 1 plus 9 over 4 x. Yes. Can I take the square root of that? Yeah, but to do the square root, I have to do the square root of the whole thing. I can't just do it in pieces, right? So there's no way to break up or factor out 1 plus 9 over 4x to get it as a square to get rid of the square root. So there's really, at this point, no way for me to simplify down this square root. So we can't simplify. All right. Can I use substitution?
Yeah.
All right. Let's try it. See what happens. So the nice thing is use substitution really doesn't take long to try. So what would we want to make u in this situation? All right, so if I make that 1 plus 9 over 4x, the du would be just 9 over 4 dx, right? And that's fine.
Use yellow
Oh.
instead of red.
I did use yellow, actually.
That's yellow?
Yeah.
Never mind.
Like, I did use yellow instead of red.
Hold on, you put down the glass.
That's red. Is blue better?
It's all good.
Okay. All right. So as long as my u substitution doesn't have an x left over in it or something left over in it that I don't have, I can do it. In this situation, I don't have any x's left over. So I can clean this up pretty easily. So I'm going to move that 9/4 over. So I have 4/9 du equals dx. So I had u was 1 plus 9 over 4x. du, or 4/9 du is my dx. So I've got that. I can change the 1 and the 4 if you. So this is one of the situations where you can change the 1 and the 4 because we're doing a definite integral. So you don't have to go back to x, or you can just leave it. It doesn't make a difference. All right. And actually, in this problem, doesn't really save you much time either way. So I'm just going to leave it as the 1 and the 4, and then we're going to go back to the x at the end. So I have the integral of the 4 of the square root of u, which I'm actually just going to replace that as u to the 1/2 du. And then I have the 4/9 u to the 1/2 du. And then I have the 4/9 out in front. So what's the integral of u to the 1/2? So I have u to the 3/2 over 3/2. So flip that over. So I've got what, 8/27, and then 1 plus 9/4 x to the 3/2. And we're going to evaluate that from 1 to 4. Any questions on what we got to there? So the 8/27 comes from 4/9 times 2/3. Because you flip that over at the bottom. And then I just replace my u back with the x to do my piece there. Now I got to plug in 4 and 1. So we've got 8/27. I plug in 4, I get 9/4 times 4, which is 9, plus 1 is 10. So I get 10 to the 3 halves minus. If I plug in 1, I get 9/4. 1 plus 9/4 is 13/4. So I have 13/4 to the 3 halves. And there's not much simpler. You can write it. The book breaks it down into 10 square root of 10 and things like that, but you really don't have to. So if you throw this into Cosmos to get an approximate answer, because one of the things when you're doing calculations like this and you're actually going to use it, an approximation's probably good. Now, depending on how you're going to use it, depending on how much of an approximation you're going to need. What we found was the exact answer. The approximation would be 7.634 if you went up to 3 decimal places. So the question is, if that was a straight line, what's the length? It would help if I switch back over to the screen. If that was a straight line, what would be the length? Just do it from 1 to 1 to 1 to 4/8. So we got 3 squared plus 7 squared, right? So 9 plus 49 is 58. So what's the square root of 58? Yeah, 7.61. So that's pretty close. Okay. A straight line would be y equals x. That would be a straight line. So y equals 3 halves, or x to the 3 halves is slightly more, a little curve. So, but that's one of those things where, depending on the shape, that would help you get a good idea if you did your work correctly. So you want to come up with a way that you can check your work. One of the problems this morning in my stats class, we were doing numbers from 5 to 80. And he found a standard deviation was 963. And he's like, well, that's what the calculator gave me. And I'm like, absolutely. Does it make sense? And it's like your standard deviation tells you variance. You can't have something that's basically 10 times what any of your numbers are. It doesn't make any sense. So that's where, like, when you're looking at things, when you're getting numbers, you want to make sure that they make sense. So we can do a quick calculation on this one just for the actual straight line, and this is pretty close to that. So you probably have it right. All right. If the shape was a little crazier, we might have to do a little bit more calculations to check it. But you want to get a general idea of, does your answer make sense for the problem? Okay. Because if you screw up, the odds are you're going to screw up bad enough that this is not going to be close at all. Okay. You're not going to make a little mistake in here that's going to get this answer to be very, very close to what you're supposed to have. All right, so that's can help you when you're doing your work. All right, let's find this one. So that's the shape we're looking at. And they gave me x equals y squared, and we're going from 0, 0 to 1, 1.
But this one is easier to go with the other formula, right?
Yeah, so this one's solved already for x. So let's use the y. We're going to do the dy problem for this one because it's solved for the x. So we're going to do the integral from a to b of 1 plus the f prime of y squared dy. So we've got f of y is y squared. So what's f prime of y? It's 2y. You're doing the other direction. That's honestly, remember what I said before, like the algebra is typically the thing that you're going to screw up. Now you're getting to the point where the most common mess up that you're making is actually less on the algebra, and it's more screwing up the direction on the power rule. Because they're very similar to each other, and you have to figure out which direction you're going to remember it. So it's like that is a very, very common mistake that you're going to make. All right. So we've got our f of y. So let's plug in my thing and look at my equation. So we're doing this one. The nice thing is this one, the x's and the y's are the same. So my range is going to be 0 to 1 no matter what. We've got 1 plus 2y squared dy. So if I clean that up a little, we have 1 plus 4y squared dy. Uh-huh. All right. So now when you're looking at this, again, same process that we were doing for 7.5. Can I simplify this anymore? If it was 1 minus, I might be able to do something to it. Actually, in this case, it really wouldn't make a difference with the square. So that's not going to help. If I look at u substitution, if I make u 1 plus 4y squared, I'm still going to have a y in there, right? I'm going to end up getting du equals 8y. And I don't have an extra y out there to pull it out. All right, so we can't do U substitution. So what's the process that we use when we have square roots with things inside of them that I can't do anything with? I have to use trig substitution. So let's remind ourselves what trig substitution is. That everybody's like, chapter 7's over, I can forget about this. Yeah, no, it's not the way this works. All right, so here's my trig substitution. Which one am I going to use? I have the plus, right? So we're going to use this one. So my x is going to be a tangent theta. A is 1 in this case. Actually, a is not 1 in this case. So we've got, we're going to make y is a tangent theta. My a, again, remember we have to get rid of, make it so something cancels itself out. I want to get rid of that 4. So when I square it, I have to get rid of the 4. So what's squared is going to get rid of the 4. It's 1/2. So a is going to be 1/2 tangent theta. So the goal is to get this as just 2 simple squares. So it's 1 plus the y squared. So I need to get rid of that 4. So if I multiplied it by 1/2 squared, which would be 1/4, the 4 disappears. So that's the goal. All right, so that's y. So now I have to find my dy. So what is the derivative of tangent? Secant squared. So I have 1/2 secant squared theta d theta. And let's do our little square root cleanup here, and then we'll plug. Oh, I got to find the 0 and the 1 too, because I'm not going backwards. So we have 1 plus 4 times 1/2 tangent theta squared. So I have 1 plus tangent squared theta, which is secant squared theta, which is just secant theta. All right, so let's also figure out the 0 and the 1. So when y is 0, I have 0 equals 1/2 tangent theta. So 0 equals theta. Get that up a little bit because I need the space for the other one. So if we did 0 equals 1/2 tangent theta, 0 equals theta in this case. Because tangent theta equals 0, the value that is theta has to be 0. If I do 1 equals 1/2 tangent theta, it's 2 equals tangent theta. So that means the arctangent of 2 equals theta. Because I don't want to have to go back to the y's at the end.
Oh, okay, you're plugging in.
Yeah, I'm plugging. So this is the those. Because if I remember to go backwards, I have to do the whole triangle thing and everything else to go backwards out of it. And that's actually going to cause me more work. So in the last problem, I didn't do it because it didn't really save me any work. This one's going to save me work. Even with the arctangent of 2, that sounds kind of crazy. I'm going to make this right here, instead of having to continuously write that, I'm just going to call that, well, actually, let's not use A because I've already used A. Let's call that M. So it's going to be 0 to M instead of 0 to the arctangent of 2, just so I don't have to keep constantly rewriting the arctangent of 2 over and over again in my integration. You can do that. That's as long as you label what you're using, so this way I can look at what you're doing, you're fine. Yes.
Sorry.
That's okay.
Where did we go? What are we doing?
Okay. My goal at this point is I have to fix my integral to do something, get it to a point where I can use it. Okay. So I need to take this and make it something I can use.
Yep.
So I need to replace everything. In essence.
Yeah.
So I made y 1/2 tangent theta.
Yep.
Okay. We took that, we plugged it in and cleaned up my square root. So my square root's at secant theta.
Yep.
So I no longer have my square root. I now needed to replace dy because I have a dy. So I took the derivative of that, got that. Okay?
Gotcha.
All right. Now, those are still in y's. I need those in thetas. So 0 is y equals 1/2 tangent theta. So 0 is theta. What's tangent of theta equals 0, and what's the arctangent of 0? Is 0. Same thing here. I have 1 equals 1/2 tangent theta. Multiplied by 2 to get rid of the 1/2. Unlike this one, it doesn't disappear. So 2 equals tangent of theta. Now this one, I don't have an easy on my unit circle what 2 is for tangent. So it's just the arctangent of 2 equals theta.
Gotcha.
Because I don't have an actual specific value for it. It's not like if it was pi over 3 or pi over 4, like I would have an actual value that I can plug in. This one I don't.
Gotcha.
So instead of having to rewrite, because now this is what I'm going to write up there as my ranges. Instead of having to write arctangent of 2 every single time I write out my integral, I'm just putting out.
The dy screwed us all up and we have to do this whole function thing.
Yes.
Gotcha. So instead of 1, it'll be the arctangent.
Yeah.
Gotcha.
All right. Now that we've got all that, we can rewrite our problem. All right. So we have 0 to m. We have the square root was no, the m was 1.
The 1 turned into 0.
No. The 0 turned into 0. The 1 turned into m. Yeah. So it's still 0 to 1. All right, so the square root became secant theta. And my dy became 1/2 secant squared theta. D theta. So I now have 1/2, 0 to m, secant to the 3rd theta, d theta. And before anybody accuses me of always picking the hardest problems to go through, this is actually example number 2 in the book. I didn't pick a random problem. It's literally the one they did in the book because this is not done yet. All right, we have one of 2 ways we can do this problem. One way is I can go through and do the rest of the problem out. The second way is we can see how good your notes are. We've done this problem. So do you want me to do it again? Or do you want me to use your notes that you've already done? Your choice. Do it again.
This isn't one of those where you pull out like the odd, like,
No.
okay.
This is one of those ones that's going to actually double up on itself. It's going to rotate back to the secant to the third actually in the integral. All right, that's fine. We can do it over again. It's not the end of the world. It's good practice. Don't worry. Here, I'll show you. My last class had to do the same thing, so you're fine.
Same question?
Yeah, we did these. I used the same thing over and over again. So my last class last semester or in the spring of last year had to do the exact same thing. They didn't have it in their notes either, so we had to redo it. All right. So when you have we have secant to the third, but we don't have a tangent. So I can't do those trig rules where I have the other things to be able to kind of cancel stuff out. I don't have another tangent here to be able to do that with this. So we actually have to do this by integration by parts as a product. So I need to split this up so I have two things to use for. So we're going to split this. So this is secant squared theta and secant theta, d theta. And now I have to do my u du. And because these are long, I'm just going to write them underneath each other instead of next to each other. So we're going to set u to be this secant theta. And that means dv is secant squared theta. D theta. So what's the derivative of secant theta? Secant theta, tangent theta. And what's the integral of secant squared theta? Tan theta. All right, so we now have 1/2 times this whole thing. So it's uv, so it's secant theta tangent theta minus the integral of tangent theta times secant theta tangent theta d theta. All right. So we are now here. Okay, so let's deal with this part over here. So I've got the integral of secant theta tangent squared theta d theta. Oh, no, backwards. This is just secant theta. Minus 1 or plus 1? It is minus 1. Okay. And they did a bunch of little steps in that. So this step was, I just put the, please don't step this up together. You could go through and do this, or you could try to go through and do this with the tricks of that trick, the trig integral. Doesn't come out to be that nicely done though, actually. So one of the other options, and it's, remember, whenever you're playing around with trig, there's identities to allow you to change things in others. So in this one, I could change tangent back into secant. You're like, well, why would I want to do that? Because if I have secant, again, now I have that secant to the third again. I can pull that over to the other side and then divide the whole problem by it. Like I did with the e's and stuff like that, and did a couple of those problems. And then I just have to deal with this integral of the secant thing. That's just a rule. Okay? So that's going to save me some work. And that's really one of those things that, unfortunately, there's no real easy way to just remember to do it. It's just playing with problems over and over again to see patterns. Okay? So it's not something that I would expect everybody to go, oh yeah, let's just change this back there. It's going to work out great. No. I've expected you to try a few things to try to figure something out that might work. Okay. Unfortunately, that's where the more problems you do, the better you get at noticing those little patterns and stuff that come up. All right, let's finish this one up.
Did you
Which one? This one? This one?
Yeah.
That's right there.
Also,
Yeah. Yeah. I just multiplied. It's all multiplication right here. I took the secant theta and then the tangent squared theta. Every so often, I don't know why it doesn't pick it up. Like there must be something with the speakers. Every so often, I hear a slight echo of my voice. All right. So what we in essence have now is the integral of secant to the third theta equals 1/2 secant theta tangent theta minus 1/2 the integral of secant to the third theta plus 1/2 the integral of secant theta.
Oh, you didn't make it.
I literally just did it for all of them.
All right.
So 1/2 times this, 1/2 times this. And it was the negative sign from there, so that's where the negative sign came from. And then it was the 1/2 to this one. And it's positive because the negative and the negative.
So I'm gonna cancel out. There's like a half on the other side here.
Oh yeah, I did have the. Wait, where was this?
Yeah.
That makes it a little bit.
Yes. So it's still gonna end up being 1, which is nice. All right, so if I add this one over the 1/2 secant to the third theta over to there, that just becomes, huh? It's just 1. So I have what I now have is not as much of a mess as it sounds. So I have the integral of secant to the third theta equals 1/2 secant theta tangent theta plus 1/2 the integral of secant theta d theta. I remember. Yes. So what is the integral of secant theta? Does somebody find me the rule? Okay. The natural log of secant theta plus tan theta? Okay. Oh, I forgot the 1/2 in front. Huh? That's just a rule. If you look at the list of rules, the integral of secant theta is just, that's the rule for it. It's like knowing the integral of sine is cosine, or negative cosine. It's just one of those things that you just kind of have to memorize. That's why I just asked somebody to look it up or find it for me, because I didn't have it memorized. All right. So I had, my original problem was 1/2 the integral of secant theta, squared theta, or to the third theta. That's the original problem I had. And it was from 0 to m. Correct? Okay. So my answer to this, before I have to go through and do all the workout, is 1/4 secant theta tangent theta plus 1/4 ln secant theta plus tangent theta, all evaluated from 0 to m. Huh? Why is it 1/4? Because
I canceled out.
it didn't. It didn't. No, it canceled out. Remember, we're looking for, we were finding the actual integral of or secant theta. By adding it back over, it gave me the integral of secant to the third theta. I wasn't originally looking for that. I was looking for 1/2 of that. So because
So you
we,
have to double it?
no, because we put in, when we took,
you have
we,
to half.
right, we have to half the thing.
Right, that's-
If you, so this is one of those situations where if you didn't actually do this step here, if I didn't put the 1/2 here, when I brought it over, it would have been 1/4 to begin with.
Before you move it over, can't you just cancel the whole term and then you're just adding 1 side?
Right, and then you're
So then it's 2. Oh wait, then yeah.
right, and I still have to divide.
Never mind.
Right, that's what, it's still going to come out to be end up being the exact same in the end. All right. So, not quite. He's lost to something different. All right. Huh?
So is it like if you added it there and canceled it out previously, when you added it to the other side,
It's because that's what we went for.
double the two theta.
I would have still divided everything by 2,
Yeah, but
and I got in 1/2. And you would have had the integral of secant to the third theta equals the 1/2, exactly what I had there. And I still would have had to put the 1/2 back because I was really looking for 1/2 the square, the integral of that.
but
You can't, I know it,
can't cancel it out from outside. Of the
right, no.
So you're not looking. You just like are looking at just the integral and not what the half is on the
Yes.
outside. So you actually can't cancel it out.
No, you can't cancel it out across the whole thing.
Wait, the long story short, right? You added
This is right, long story short.
So you added 1/4, right? Just to get the 1/2. On the
My original problem had 1/2, was negative 1/2 the integral from 0 to m of secant to the third theta.
So in order to plug this into that, you need to have it.
Right. So my original problem was this. When I went through and did all that extra work to find the integral, I found that. Okay? But I wanted half of that. That's why I had to put the half to multiply out that side by the half. That's where the 1/4 came. All right. We're almost done with this problem. We would be done if it was an indefinite integral. Actually, we'd have to go back to the x, or in this case, the y. But now I can actually do our calculations.
Going backwards, the half is, we did the u continental of d here.
Yeah.
That.
Mhm.
And didn't pull the half all the way through. But
Okay. So this is the original problem I was doing.
yeah,
So that's what I'm trying to find. Okay. Because I'm not going to keep walking back and forth. The beauty of mobile. All right. So we're going through and doing our calculations out, no problem. There you do you, found our integration, and this is what I have here. Okay. I was originally doing that problem, which equals this problem right here. Everybody good to that point there? All I did was I distributed this 1/2 to that and those two pieces. So 1/2 was on everything. The reason I did that is because if I didn't, when I tried to pull out the secant, it was going to cause more trouble with you because you were going to try to figure out why I pulled out a half when it wasn't a half in front of it. Okay. When I add the 1/2 over here, this now becomes a full integral secant to the third theta. Because I had 1/2 here and I'm adding another half. So that now becomes 1. That becomes now the integral of secant to the third theta. Okay? So that's my integral right there. So secant to the third theta. But the entire process of doing this is one of those tricky things when you're moving things over, and it has to be the original problem that we were looking at. Otherwise, that's not the integral. This wasn't the original problem that I was looking at.
But why is it won't be? We're looking for the length of the thing, but if you're using that integral, that's twice of the length of the thing. So
Right.
you have to divide it by half to find the actual.
Because my integral that I was looking for was 1/2 of that. So I got to take this whole thing and multiply it by 1/2 because I only wanted half of that.
so that upper portion, like section of the original problem,
Yes.
not
It's helping me come up with what this is. So it found what that part right there is. it didn't take into account that 1/2. Because there's no 1/2 out in front of this. If there was a 1/2 left in front of it, I'd be good, gold. But there's not.
Oh, okay, so the previous section is only half the problem.
Yes.
Like 1 point.
Okay. Practice. I'm dead serious. I'm not even kidding.
Yeah.
You have to practice this stuff. I guarantee you, I haven't looked at your test yet. But based on what I'm seeing in front of me right now, I have a good idea of what I'm going to see on this test. 7.5. Section 7.5. Practice it. Yeah. So you need to, that's why we did, as crazy as it sounds, why we did chapter 7 when the problems are broken up. When we move into chapter 8, it's now application problems. Application problems aren't always nice. And to be honest, when I hit 8.3, those problems are worse. When we actually look at, like, we're looking at arc length, which, yes, is a realistic problem, but it's still an algebraic problem. We're still looking at a graph, finding an arc length of a line. Okay? And when I go on Thursday, we're going to look at surface area. We're going to take the arc length and rotate it, and we're going to find surface area. It's still theoretical in essence. 8.3, 8.4, and 8.5, of which I only ever do one section. And the only reason I'm doing 8.3 is because more than half the class is like engineers and physics type majors and stuff like that. And so that one fits them. Otherwise, it's biology or probability. Probability is the one I normally do if nobody else really cares, just because I know that one. But we're going to look at the pressure on a dam at different lengths of different things. So you're looking at hydrostatic pressure, or you're looking at centers of mass, looking at being able to balance something on the tip of a pin. Where are you going to put it to balance that? Like, those are actual realistic problems that are done every day. So they're not the simplest of problems to deal with. And that's why I said you have to practice the, as crazy as it sounds, the easy stuff in section 7, chapter 7, before we start doing the stuff that combines it all. Okay? So yes, this is one problem. And it wasn't a problem that I necessarily chose. It was the example 2 in the book. It's literally the second example in chapter 8. Okay? So it's not necessarily meant to be the easiest problem, but it's meant to get you an understanding of what could be involved in some of these. All right? We're actually almost done. We have one left to do. We just have to find theta and plug in the numbers and get the answer. So this was to M. And M was the arctangent of 2. All right, so I need to find out what theta is. So in this case, theta is the arctangent of 2, if you remember right, for that one. And I have the 0, which we'll do that one too. So tangent of theta is 2, correct? Okay. Notice, I'm trying to find these, so I can just plug them back in and find it easy. Tangent of theta is 2. So when I plug in my tangent of theta, I can just replace it with a 2. I don't have to replace it with anything crazy. What's secant? Well, I know that secant squared theta minus 1 is tangent squared theta, right? So secant squared theta minus 1 is 4, right? So secant squared theta is 5. So secant theta is square root of 5. Okay. All right. So we have. I'm going to pull out the 1/4 just because I don't feel like dealing with it constantly through the whole problem. Secant of that is square root of 5 times 2 plus the ln of square root of 5 plus 2. Minus. So now we just basically plugged in what we had for each of those. What's secant of 0? What's tangent of 0? 0. So that whole thing's gone. Because 0 times anything is 0. What this one we kind of would need what secant of 0 is. So just plug in your calculator secant of 0. Should be 1 if I remember right. Because cosine of 0 is 1 and secant's the reverse of that. So it should be 1. So 1 plus 0 is 1. What's ln of 1? Ln of 1 is 0. So that's 0. So I have 1/4 times 2 square root of 5 plus ln square root of 5 plus 2. And that's my answer. Really? Now she's being sarcastic. No, I'm just kidding.
I'm trying to be
It will when you get past the I'm completely overwhelmed by how many steps was involved in this one problem.
It's like I get it in chunks.
No, I just put the 1/4 in the front.
For me, it's not that, it's just the fact that there's so many steps I could mess up.
Absolutely. No. And that's what I said. When you get past like the overwhelming amount of steps that there was, if you start to break it down and look at each piece, you will figure out what's going on. All right. And that's where I go back to the chapter 7 thing is that we didn't do until the very end when I screwed up one of those problems, a problem that was massively long and involved multiple different ways to do it. Like this one problem involved trig integration. It involved integration by parts. It involved a bunch of different steps. Okay, all in one. So that's going to happen with some of these problems. Not all of them, but it can happen in some of them. Yeah. The 0. Basically, everything else canceled out except for the ln of 1, which ends up being 0. So the 0 ends up canceling it all out anyway. So that's why that disappeared in the final step. All right. We got one more thing we have to do. It's not overly difficult. So far, the two problems that we've done found me an exact answer. Okay. So I think it was a little blurry. There it is. You'll notice that this equation is very similar to the equation we were just doing, with one very distinct difference. Anybody notice the one big difference, other than the fact that it's in T's? Which I hate. Huh? Right, we don't have an endpoint. It goes to X. Okay? Sometimes, actually quite often, you're going to want to do a problem for the entire problem. And then you can use it to find different pieces of it that you want. Okay? So say I have this curve as y equals x squared minus 1/8 ln of x. So it's this nice little annoying equation that you think is going to be very difficult, but it's actually going to work out kind of nice. So we've got this problem there. And I want to know, I'm starting at 1, 1, and I want to be able to figure out the length from 1, 1 to 10, whatever the number happens to come out to be. And then I also want to find from 5 to something else. Like, I want to find a bunch of different arc lengths off of it. It's going to be easier to find me an equation that I can just plug numbers into it, instead of finding me doing the same thing over and over again to find all those values. All right. And that's where this comes in. The only difference is the very end. We're going to come out with a function instead of a specific number. So it's still done as a definite integral, even though it's kind of got that, in essence, of an indefinite kind of function. Okay. Huh? Yeah, we're basically going to plug in x at the end. All right. So actually, let's do this. All right, so we've got our function. We know that y is x squared minus 1/8 ln of x. I need my what? I need my y prime. I need my derivative of it. So what's the derivative of this? 2x minus 1/8 what? 1 over x, right? Because ln of x becomes 1 over x. So it's 2x minus 1 over 8x. All right. So let's look at this square root. So if I plug this in, my square root, I'm going to have 1 plus 2x minus 1 over 8x squared. So on its face value here, it doesn't look like I can do an ICU substitution or anything else like that. It also really doesn't look like what I had in my trig substitution with 1 plus just a square. I have this crazy function inside that square. So let's see if we can simplify this down a little bit. What's something you'd like to try for this one? Yeah, let's FOIL it out. See what I got. So if I FOILed this out, let's just do this on a different screen. So I had 1 plus 2x minus 1 over 8x squared, right? Yeah. All right, so 1 plus, so that's the same thing as saying that times that. So 2x times 2x is 4x squared. 2x times negative 1 over 8x is negative 1/4. Negative 8x times that is going to be another negative 1/4. And negative 1 over 8x times negative 1 over 8x is negative 1 over 64x squared. Oh, yeah, positive. So I have 4x squared plus 1/2 plus 1 over 64x squared. Okay. Is that a perfect square? Yeah, that's 2x times 2x, right? Is that a perfect square? Yeah. All right, so if I change this to this is just a try to see if it works. Yeah, there's a positive there. One minus 1/2 is 1/2. All right, so that's there. Does that give me 1/2 in the middle? Because I know it's going to give me the first and the last part, right? Is it going to give me the 1/2 in the middle? Well, it's 2x times 1 over 8x is 1/4, right? So I have 1/4 plus 1/4 because I have to do it twice, which is the 1/2. So it does. So congratulations, I have that. So my whole square root is that. So it's the square root of 2x plus 1 over 8x squared. So that's just 2x plus 1 over 8x. This is where, when we originally looked, I'm going to switch real quick and I'll switch back. At the problem, we're like, yeah, that looks messy. But a little simplification. Now I have something that doesn't look so bad. The half was foiled. So if we foiled out 2x plus 1 over 8x, it would become 4x squared plus 1/2 plus.
Oh, okay. I just got it.
Well, yeah, because one of the things that when you're looking at trying to get it to be a perfect square, which is what I was doing in this case, the a and the c, the beginning and the end, have to be perfect squares. So 4x squared was a perfect square. 1 over 64x squared was a perfect square. So you do those and then see if it gives you the number in the middle. If it didn't give you the number in the middle, it doesn't work, and we can't factor it out. This one does give me the number in the middle, so I'm good. All right, so let's go back to my little problem here. So my integral is going to be from 1 to x. And this whole thing I just did is 2t plus 1 over 8t dt. So what's the integral of 2t? It's just t squared, right? What's the integral of 1 over 8t? Yeah, it's 1/8 natural log of t. And we're evaluating that from 1 to x. So if we plug in x, I get x squared plus 1/8 ln of x. And if I plug in 1, I get minus 1. Because it was 1, because they gave you the point. They wanted you to start at 1, 1. And I know we don't do it very often where there's actually something left over on the other side. So this is the x version. And then that's actually the minus the 1. It just ends up being that one because ln of 1 is 0. So this part is. So that's where the minus 1, the x minus 1. That's fine. Believe it or not, the two problems we did, the actual process and steps for finding arc length are identical. The integration was a lot more difficult with example 2 than it was in example 4. But if you looked at that original problem before we did actually simplification of it out, it looked way more complicated than even started with the other one. Because the other one was literally just 1 plus 1/2 x squared. It actually was a really simple looking problem. And so it made a lot of work to go through it. So don't necessarily look at the original problem and go, oh, this was going to be easy because it's simple, and oh, this was going to be hard for the things. That's where the simplification steps is. That's where the substitution. That's where we're looking at it. Like, let's see what I can do to make this problem easier for myself than hard. Right? And like with this one, it's not quite simple. Now we can technically plug in any value I want for x and find arc length. I know it just it changed slightly. Yeah, it didn't change much. Well, actually, even if we looked at this, my original derivative was 2x minus 1 over 8x. And after I did the whole thing, it ended up being 2x plus 1 over 8x. So it really didn't change by much. So LNs have a tendency to do that. All right, so 2 things. First, if you are having trouble with the actual integration steps, chapter 7 or section 7.5 is your friend with that one. I wouldn't do, like, if you know you're having trouble with the integration, with the trig integration or the trig substitution, go back and do that section specifically if that you know you only want to work on those. Section 7.5 mixes them all up. Okay, so you have to look at the problem and figure out what to do, which I think is helpful because that's what you're going to have to do going forward, and everything else we're doing is figuring out what you're doing and then doing the integration, because it's not going to be, oh, we're always doing this type of problem. All right. I also then would practice some of the stuff in 8.1. Okay. Because 8.2 is very similar to 8.1. We're just rotating it. The nice thing is the formula incorporates that in, so you don't have to find necessarily the arc length and then do it. It's just all integrated together. But the formula becomes a little more complicated. Maybe I didn't do that one. I might not have. That's possible.